Thank you everyone for coming. Today my talk will be about geospatial analytics at scale with deep learning and Apache Spark. I was supposed to do the talk with Tim Hunter, who couldn't make it today, so I am the only one on the stage today, so please bear with me. So I'm going to start off with a brief introduction of myself. My name is Wang. I'm a solutions architect at Databricks, and I've been at the company for about 4 years now. And I specialize in machine learning solutions. So what that means is I work with our customers to build scalable machine learning applications, and most of the time that is with Spark. So what will this talk cover? So the three main topics that this talk will cover would be image processing with Spark, so how you would ingest images with Spark and how you would work with image data. And a second main topic would be about object detection with transfer learning. So I'm actually using a pre-trained model that was trained on a similar data set. And I'm going to run geolocalized queries to kind of do a little deep dive in the prediction results that come out of the model. And I'm going to do that with Magellan. And then right at the end of the presentation, I'm going to run through a little demo. So mapping the world is arguably the most ancient big data and data science activity in the world. So back in the day, you would send your ships out. And people would kind of draw the maps out manually. And if they actually come back to you, if they make it back to you, you get to collate the data set and you update your data set. And that is crucial for several reasons, and most notably of which is having proper maps are crucial for navigation, for warfare, and also for commercial reasons, figuring out who your trade partners are and who the trade routes and things like that. So fast forward to today, we've seen a lot of evolution in how we collect that data in the past 2 decades. So people have been using drones, airplanes, satellites, and it has kind of evolved from having someone in the field to do like manual surveying and taking manual photographs and things like that. So things have become increasingly automated. And as an example, if you take a look at the picture on the right-hand side, that's actually a satellite from Planet Labs, which is, if I'm not wrong, based in San Francisco. And they have more than 80 of these satellites, taking pictures of the world daily. So you can only imagine, the amount of data that is generating. So with richer data sets, we have new interesting applications. For disaster recovery, we can detect floods or figure out if an area is prone to flooding or if a tree has fallen and is blocking a road. And for infrastructure management, we have, you could detect potholes on roads and things like that from satellite imagery. The last one is interesting because we've recently heard of a use case where you could use satellite imagery or aerial imagery to figure out if a neighborhood is suitable for installing solar panels. And this would traditionally be something that you have to set an appointment and someone would come to your house to do an inspection, measure the roof and things like that to figure out if your house is suitable for solar panels or not. And now you can actually have a drone survey the area, and then you can figure that out for the whole neighborhood, and it has become a data science problem. So with richer data and new interesting use cases, it also introduces new challenges. And the first one is something we're all familiar with. With larger data sets, how do we process that data in a most cost-effective manner? And with images, it's interesting because, well, the technology is improving and we are collecting more data, and also the resolution of the images we're collecting is higher and higher in resolution. So it quickly becomes a big data problem. So the second point here is traditional geospatial tools are not meant to scale. And by traditional tools, I'm referring to technologies like PostGIS, for example, which was just not built to scale to process petabytes of image data. So how do you actually move your analysis to, to the whole neighborhood, to the whole country, or to the whole world? And the last challenge here we would like to point out is what we call a pipeline challenge. And what a pipeline challenge means is, for a use case where you're trying to do object detection within a satellite, within a JPEG image, for example, there is a lot of different tools that you have to use. So for geospatial analytics, you'll use your geospatial package. And for image processing, we have a different set of tools to kind of resize the image or do color corrections and things like that. And then you have another tool for, say, the deep learning stuff. So how do you actually bring all those tools together? And traditionally, those tools exist in silos, and that has been challenging. So today's example, we are working with satellite images, and our goal is to identify vehicles within our JPEG images. And it looks something like this, where this is a sample JPEG image, and then we're going to pull out the buses, the trucks, and the cars. For the demo, we actually filtered down to cars only, just to narrow the scope of our demo. And interestingly, we are able to pull out quite a few interesting insights based on just cars. So we've spoken a lot about the challenges we will face. And then the next thing is, how can Spark address those challenges? So we see Spark as the glue of big data technologies that exist in isolation. So addressing the third point in the previous slide, we have, say, OpenCV for your image manipulation. For deep learning, we leverage the popular packages like TensorFlow, Keras, PyTorch. And then for geospatial analytics, we have, say, PostGIS or GeoMesa. For this demo, we're using Magellan, which is a geospatial package based on Spark. And then for visualization, these are the two packages we're using for the demo. But as everyone knows here, there are several packages out there for visualization. So Spark can tie all of these libraries together at scale, and you can wrap these packages in a Spark UDF and distribute it across multiple machines. And it allows pipelining in the sense that you don't have to worry about how you're going to transfer the data from one package to another, one tool from another. You don't have to worry about how you're going to store that data or the intermediate data representation. And we can kind of look at that pipelining within the demo later today. So here's a visual representation of the pipeline we have. And we start off with JPEG images, our map data. And it comes with XML metadata. And what we're interested in the metadata is the coordinate information. And we need that primarily for visualization purposes. So we have map data of, for London, actually. So we've got our data set from a customer of ours, Ordnance Survey, which is a national mapping agency in the UK. So we've got our map data from them, and it's the map pieces that we got off London. And so we have corresponding XML metadata. And we're going to do a simple Spark join here to just combine the two. And we're going to do some transformations with UDFs. So let's take a deeper look into that. So for ingesting the images, we're using Spark. And with Spark 2.3, we've introduced a new way to read and write image data with what we call the image schema. And with image schema, it makes it really easy to pass that data along across packages. So this schema can be used with packages like scikit-image or OpenCV, PIL, which are very popular open source Python packages to process your image data. So right at the bottom there, I have a little code snippet on how you can read in your JPEG images, a whole directory of JPEG images into a Spark data frame. And then let's talk about the transformations we're doing here. So the first is combining the images with the XML data. And again, this is primarily for visualization purposes. So we need to figure out which map piece if we've identified a car within a JPEG image, how are we going to plot that on a map? So we need the coordinates to do that. And then the second transformation we do is a simple coordinate transformation from eastings and northings to latitudes and longitudes. So for those in the room who were like me, who don't know what eastings and northings are, we actually got our data from UK mapping agency. So all the coordinates on this British way of recording coordinates, so they're in eastings and northings. And every popular plotting library out there uses like latitudes and longitudes. So we had to do a little conversion to get that done. And then the second transformation we did was actually to create image chips, and we have to generate the respective coordinates for each image chip. So to explain what that means, on the left-hand side, we have a JPEG image. So that's the sample image that we're working with. And you can see that there's a lot of information within each image. And these images are coming in a 1 kilometer by 1 kilometer square. So there's going to be a lot of information and objects within each image. And we're going to run into hardware limitation here. So you might need to spin up a huge machine with a lot of RAM and CPU to kind of do that, to handle that kind of processing with your deep learning model. So what we did was we actually sliced it up into smaller pieces. So for every image we had, since it was a 1 km by 1 km square, we sliced it up into 100 smaller pieces, and a smaller slice, what we call an image chip, is what we see on the right-hand side of the screen. And in order for visualization, we have to generate the corresponding coordinates for the bottom left and top right corner of each map piece. So that's the transformations we did in our demo. And once we're done with the transformations, we're passing it into a pre-trained TensorFlow model. So we've seen a lot of success with deep learning for image-based applications. And I'm sure there are multiple talks today that addresses how you distribute TensorFlow for, say, object detection or some kind of other deep learning use case. And what this means is there are a lot of pre-trained models out there in the same domain that we can leverage. And what we did today was we actually used a pre-trained model in what we call the XView challenge. I'm just moving here. So this is the XView challenge, which is an object detection challenge that was organized by the US Department of Defense, actually. And it released a sample data set which kind of looks like this, which looks slightly different from what we're working with. And as part of the challenge, they also have a pre-trained, here we are, a pre-trained baseline model that they use TensorFlow with the object detection API to train. So we're actually just downloading that model, and we're using it for our data set to figure out how well it does with object detection with our data set. And to do that, we used, I'm just going to skip over that slide. To do that, we used this package called Spark Deep Learning Pipelines, which allows us to load that persistent TensorFlow model, and we can generate, we can run model inference at scale with Spark, and we can take a closer look during the demo today. But the key takeaway here is Spark Deep Learning Pipelines was built with ease of mind and Spark integration in mind. So if you're familiar, say, with MOLIB, it has a pretty similar API and syntax. And we support Python, and so that's in line with the popular deep learning packages out there in open source. So once we are done with our object detection pipeline and we've we will get a list of objects identified and the corresponding class of each object. The next thing we will do is to do a deep dive into our prediction results to see how well our model did. And we did that with a geospatial package called Magellan. And the idea here is to run a geolocalized query in a certain area to see if the cars we've pulled out from our JPEG images are really cars or not. So common geospatial tasks, finding all objects within an area, which again is what we did here. We specified, say, a coordinate boundary, which we created a polygon for, and then we're going to find all cars within that polygon. So that's a very common geospatial task. Other very common geospatial tasks are like, aggregating, say, the number of roads across all JPEG images, and then you can do a simple count. So that's something that is supported with popular geospatial packages as well. So why did we choose Magellan? Magellan gave us the capability that we were looking for, and it's also open source, and it supports formats like GeoJSON, and it actually integrates straight into Spark SQL, which means that the queries you run with Magellan, you get all the great performance improvements that Spark SQL brings you as well. So let's see that in action. So I'm going to toggle over to my Databricks platform. Can everyone see OK? Should I zoom in a little bit more? Great. So this is the cluster that I'm using. And let's take a look at the libraries attached. So before the demo, I've already attached the libraries I need. So things like Spark XML to parse the metadata, Magellan, Spark Deep Learning, and also TensorFlow and Keras. So I've already created that cluster, and let's take a look at a notebook. Maybe I'll zoom in a little bit more. OK, so my notebook is attached to the cluster. So you can see that over here. And the first step here is to load the data. And I'm just importing another notebook, which has a few configs that I have pre-prepared. So if we take a look at that notebook, what I'm doing is I'm just calling this notebook into my other notebook, and I'm just defining file paths here. So what I did is I actually worked on a much smaller data set for when I was developing. So I only worked on 10 images. And then I just toggled it to the other file paths when I was ready to test it in a larger data set. So that was one of the reasons why I put that in a separate notebook. So here is our data set. So I have a whole directory of JPEG images. And these images are loaded onto DBFS, which is S3 in this case. We also deploy Databricks on Azure. So if you're using an Azure deployment, that's on a Blobstore, Azure Blobstore. And this is the XML metadata that comes with our data set. And maybe I can take a little look at that file. It's a little small, but that's my XML file. I'm interested in only the coordinate information, so the other stuff is trash to me. Oops, that's my email. That is not good. So for the XML data, I've used Spark XML to load the data in. And if we scroll here, this is the information we're interested in. So it's, in this nested column over here, and you can see that as the British east things and north things. And so we have two pairs of coordinates that's separated by a white space. So the first thing we did is to convert them into latitudes and longitudes, and we have a huge Python function that does that. So let's take a look at that. And I actually took that off a GitHub repository, so I actually did not write this. And it's really long Python function just to do a simple coordinate transformation. So yeah, just So what I did was I did a string split because we have 2 pairs of coordinates, and we're going to just create a Spark UDF that calls the other function and apply that to my Spark data frame. And then this is the result. So we have the file path. Well, not really the file path. We have the name of the JPEG image and the latitude and longitude for the bottom left and top right corner in a pretty data frame. So the next step here is to load the images. And I'm using Spark to read all the images into a Spark data frame. And you can see that it's pretty cool that within a Spark data frame, you can have an image and the associated metadata within the same row in a Spark data frame. So here is where we do a Spark join to join my image data and the coordinate information. So I can have that in line with my image data. And this is where we do the chipping. And again, this is all written in Python, pure Python. And I'm not going to go through the code here, but basically I'm just iterating through the image and then creating smaller pieces out of that larger JPEG image, and then also generating the coordinates for each image chip. Same thing here, I wrap it up into a Spark UDF, and I can call that UDF on my Spark data frame here, and that will look like this. So I've generated about 60,000 chips, and this is what each chip looks like. So now that we're done with the basic transformation, I'm going to write it out into Parquet and persist that onto S3. And it's interesting to note that we're writing image data as Parquet into S3. We're writing image data and all the associated metadata, everything, just as Parquet onto S3, which is really performant, and it's into a format that's great for Spark and data science queries. So now we're going to move into the second part of our pipeline, which is how we will load that TensorFlow model in and apply it onto our transformed data set. So here, I'm just reloading the data that I wrote out. So we could restart the cluster, and I'm just loading that pre-persisted data back into my session. And here is where I load the persisted TensorFlow model into Spark. So here you can see it is a TensorFlow model. And again, this is saved onto DBFS, which is on S3. And this is just some code here to load the TensorFlow model. And here we call the TF image transformer, which is a class out of deep learning pipelines. And what it takes in as input is your input column in your data frame. So here I'm just saying that that's my column that I'm taking in as an input. And that's over here. That's the chip column. So that's the image chips. Here we have to specify the TensorFlow computation graph, which is what we loaded over here. And then here we have to just say, these are what we are expecting as an output from the transformer. Yes, question. Oh, you're asking if I can make the code available. So I was planning to release a blog post out of this whole session, and that will make the code and data available. The data probably might come from the XView challenge, so not really what I'm using today out of, since I got that data set from another source. But yeah, definitely we are thinking about releasing everything. So here again, we've called the TF image transformer from Spark deep learning pipelines. And here you see something very familiar. So we are calling a simple MOLIB transform. So that's probably familiar to you if you run MOLIB today. So we call it transform on our data set. And what it does is it gives me the detection boxes, which is basically the objects that have been objects identified within a JPEG image. And then detection classes, which is the associated class for each object, and then the scores, which is the probabilities. What we see here is, basically the input data frame, so that's already there. Cool, so now that we've run the transform, we're gonna extract the predictions. And what this does here is I'm basically just filtering our results and just pulling out results that give me a pretty high score. And that is not good. Okay, that is a bug, unfortunately. But basically, I would see each identified, let me just try and rerun that, each identified object and the associated score as well as the class. So again, as mentioned in the presentation earlier, the class is, it could be something like a car, a building, or a truck. What we're doing is we're only gonna pull out the classes associated with cars, which we know is class 18. And here we're doing a count to see, the number of objects we've pulled out from 60,000 chips. So from 60,000 chips, we have about 4.5 million objects. And now, since we know class 18 is a car, we are going to try and plot that in a heat map. So if I do a filter for class 18, these are all cars, and on just a quick look here and a quick scroll, they do look like cars, which is great. So this is the heat map, and it's good to see that we have little pockets of, higher density within London. So there are cars in the city, and if we zoom out, it's a little more interesting to see that actually this, center of London has fewer cars. So from what I've been told, there's congestion tax within the city. So there's going to be fewer cars in the city compared to other areas. And we zoom up a little more, we actually have a really high density of cars around here, which I've been told, again, actually corresponds to one of the major expressways in London. And again, I only have data set for, my data set ends at London, so I only have data for this particular area. So it's good to see that my model is doing something right. And if we do a deep dive into a certain area, so we will look at Hyde Park, which is a beautiful park in London. And you would expect that there wouldn't be too many cars in London, in Hyde Park, because it's green and there's lakes and stuff. So let's take a closer look. So here, we actually have a parking lot. So there's actually a higher density of cars in the parking lot, and there's a little bridge here with cars on it, so sounds about right. If we scroll a bit more, we also have cars in the water and cars in the trees. So that's basically, where a pre-trained model, that we're running to limits in a pre-trained model. And maybe, if you trained your own model on this data set, perhaps you'll get better results, or maybe I have to just tune the model a little bit. Great, so the next step here is to use Magellan to kind of do a deep dive into Hyde Park to figure out, what our model is doing. And here are the coordinates that we've identified for Hyde Park, and we're gonna create a polygon out of that. And we're using Magellan to do this. So we have a Magellan polygon corresponding to Hyde Park. And what we're going to do here is we're going to basically do a filter, a Spark filter for coordinates that are within the polygon. And we are only interested in the cars. So again, let's look at the cars within our polygon. And we did an order by score. So we're going to have the highest scores up here, and all of these look like cars. These actually look like they're in the parking lot, which is great. This looks like a London telephone booth. I'm not sure if we have telephone booths in Hyde Park, but correct me if I'm wrong. And if we scroll down a little bit more as the score decreases, we've got, this is something, I think this looks like a park bench. And if we scroll down, these look like tables. If we scroll down a little bit more, these actually look like cyclists. So, it's interesting to see what is being, identified as a car when actually it's another object. And again, we might be running into limitations because it's a pre-trained model, but it's also pretty cool that we are identifying, cars, and they are probably properly being classified as, as a car when it is a car. So that's cool. Great. So that's the end of my demo. And just to do a little recap. These are the steps taken for the demo. We've read in the images with Spark. We parsed that data with OpenCV and with Spark UDFs. So the transformations we did, we sliced the images into smaller image chips, and we generated respective coordinates for each chip, and this was for visualization purposes. We passed that data into a pre-trained TensorFlow model. And the model was trained on the XView data set. And we were figuring out if it did well with our data set. And the last step, the second last step was to visualize the vehicles in a heat map. And then we identified a point of interest, Hyde Park. And we used Magellan to kind of pull up the points in that polygon, basically all coordinates that fall within that boundary of Hyde Park. And then we managed to figure out if, what our model was actually doing. It's actually picking out the cars as cars, but also, say, cyclists, telephone booths, and other items as cars as well. So it's not doing that great of a job in certain areas. And that is the end of my talk. And I can take a few questions if we have any. If you have any questions, there are microphones in the central lane, and feel free to do that so that we can hear it in the recording. Take the mic. It doesn't work? That's fine. Shout it out.
Okay. So the question is, how do you deal with objects that would straddle across your time?
Yeah, that is a good question. So what we did today was very naive. We're just slicing it. So if you have half a car, that's not gonna be, that's a very tough question. So I mean, if you're interested in a particular area, then maybe you want to focus on a certain area where you're certain that there's a higher density of the objects that you're interested in, and then you have to make sure that you just cut the image data set properly. But otherwise, I agree, you'll get like half a car or like a fraction of a car.
Thank you.
So I have a question about incorporating the deep learning with Spark. So do you experience any frictions or doing that? Because my experience is I'm like, for most of the time, I just use Spark ML. So it's like kind of intrinsic Spark machine learning model. So is it, so I'm a little bit like afraid of like incorporating the deep learning into Spark. So I want to hear your comments about doing that.
Yeah, and to be honest, like in my demo today, that model was not trained with Spark. It was like probably just pure TensorFlow on a huge GPU instance or something like that. And from our experience working with customers, I would say most of them do that. They use pure like TensorFlow or pure Keras on, say, a huge machine or a huge GPU. And I use so it's like one GPU or one huge machine. And then distributed, say, TensorFlow or distributed Keras is kind of the next step. And then what we will do, what we will use Spark for is mostly for the inference, for like distributed inference. So you could, like, for example, use the TensorFlow model and then run it on a Spark data frame for distributed inference. There are ways to, say, use Spark to distribute TensorFlow, or for Keras like TensorFlow and Spark or something like that. But I would say that people usually start from running it on single node, running it on a huge GPU, and then looking at using Spark for training on a larger, like distributed setting.
So like for the current stage, like the training phase is still done on GPU, or the training phase is not done on Spark. And then the inference, once the model is trained, and then you use a trained model on Spark to do inference.
I would say that is actually a pretty common use case where the model training is done outside of Spark. And Databricks, although we are known as the Spark company, we do support training your model on like one GPU machine with no Spark at all. And then we persist it, and then we can run a distributed inference with Spark.
Cool, thank you.
Would this kind of system also be applicable to do like internal inference? For instance, if you have a high probability of something being recognized as a parking lot, then that would increase the probability of nearby things being classified as cars, if that makes sense?
Well, sorry, what
so like for instance, if you recognize an object that is high probability is recognized as a parking lot, if you're trying to recognize cars, could it internally use that to indicate there's a higher probability of cars in this area? So kind of like double layers?
So it could be a second stage of your pipeline, right?
Okay.
So the first step is to look for the parking lots, and then for the parking lots with a higher probability score, you can filter it down, and then you could run another model that looks for cars. So yeah,
just multiple iterations.
Yeah, that could be possible. Great. Any other questions? Yeah. Yeah, so I'm actually using huge machines to process the chips. So imagine if I have a larger JPEG image, that's a lot of bytes within an image, and then there are a lot of objects. So I have to use an even larger machine. It is a cluster, but because I'm running like the inference for one image on one machine, it's not going to do like half the image on one machine, and then the rest will be overflown to the other machine. So yeah, that's the biggest reasons why we are slicing it. Great. Are there other questions? Looks like no. So thank you everyone for, oh, sorry, one more.
So, back to that slicing of making of the chips. What if you have a situation where you have hotspots where, like you said, if you have a system that has too many objects in one of your chips, and so like you said, like you need to pick an area that has, you want to focus in on where your cars are, but what if you hit a hotspot where one of your chips has too many cars in it, and it just bogs down, becomes a bottleneck in the system? How do you handle that hotspot situation?
Yeah, that again is tricky, and that actually is something similar to the first question, where how are you going to slice the images if you have a car and you slice it into half? How's your model going to detect that? So again, it's partially you have to have a bit of domain knowledge in the area you're working with. You're not going to expect doing it for a global scale and then magically work. So we have to figure out, if there are areas where there are more cars, maybe we'll have to filter that out into a separate data set. So we have a data set with lots of cars and a data set with less cars, and then we have to use a bigger machine for the data set with more cars and things like that.
Kind of like a staged approach again.
Yeah.
So different phases depending on how much data you think is in each
Exactly,
chip.
and that's a very common technique we use in data processing, where you might have skews. So if you have skew in your data, it's a common technique to kind of break it down into different stages. You have a data set with the large ones, the large density ones, and the medium and the smalls. So, yeah.
Building a
I mean, you don't have to do it in one sitting. You could be, and sometimes it's not even the same team doing it. You could have one cluster running the model, training the model, and then once that is done, you could move on to the prediction or the inference stage. You don't have to do it in the same sitting. So you could also have, say, the old version of the model, and you run the inference on it, and then at the same time, you could be training a new version of the data set. So, sorry, time's up. So the next speaker, or I think it's lunch, maybe. So thank you, everyone, for coming.